Hey physics, this is Mr. Aiden, and this is the scientific models of the atom. We're going to be doing just a rough look at all of the models of the atom over time. And let's get to these old dead Greek dudes. Okay, so we have Democritus. Democritus, he lived about 400 years before Christ. Remember, in Greek times, they were just using philosophy. There was no scientific study at all until after the Reformation. And so what we see is Democritus believed that atoms were indivisible and indestructible. He thought that eventually you could keep splitting down to one complete atom, his atomos, which means that was the smallest form of matter that you could possibly have. But then there was this guy named Aristotle, lived about 350 years before Christ. Remember, he had his own school, his Lyceum school, the Peripatetic school of philosophy. He loved to play with Plato, didn't he? And what Aristotle believed is that he didn't believe in the atomic theory, in this atomos theory, but he believed that all materials on Earth were composed of four elements: earth, fire, water, and air. Boom! And so a bunny made of each one of these elements. So who do people believe? Do people believe in Democritus or do people believe in Aristotle? Well, everyone believed in Aristotle. He had the school, he had the name, he had Plato to play with. He had all these different things, and so everyone for almost 2,000 years believed in the Aristotelian view. Until a guy named John Dalton. John Dalton in the late 1700s, he put together his atomic theory, and he's known as the father of the modern atomic theory. And he put together approximately four type big theories. And his theories said that all elements are composed of tiny, indivisible particles called atoms. Is this correct? He was basically stealing from Democritus. Was he correct? No, he was not correct. Why is he not correct? Well, atoms, there's things inside the atoms. There's protons, there's neutrons, there's electrons, there's even subatomic particles of those inside the atom. But at least he came up, he took a stand, right? His second theory said atoms of the same element are identical, which guess what? He was wrong about as well, because we have these things called isotopes. We have these things called allotropes. We have all kinds of different things that atoms, even atoms of the same element, are a little bit different. They have different masses. We call that isotopes. All kinds of different things. He came up with a third theory, which he stole as well, is that atoms of different elements can chemically combine in simple whole number ratios. He kind of stole this from Joseph Proust. And guess what? He was pretty close to correct about that. We do have simple whole number ratios. There are some exceptions at different times in the definition, the clear definition of this. But think about something like H2O. There's two H's and one O. And his fourth theory said chemical reactions can occur when atoms are rearranged. So when a chemical reaction happens, we break bonds, we form bonds, we rearrange these atoms. We don't lose, we don't gain any atoms. And so there goes Darwinian evolution. Too bad. And Antoine Lavoisier came up with this scientific observation, so he stole it again. And it is a good, correct observation. So Dalton, he was batting .500, which would have put him in the Hall of Fame, but he stole a lot, which might put him in the Hall of Fame. Still, maybe not. We're trying to figure out whether steroids were. Anyway, sorry. Dalton's atomic theory looks like this. Atoms the same element, all look the same. They're tiny, indivisible, indestructible things with nothing inside of them. It's the smallest form of matter called the atomos. Well, came along J.J. Thompson. J.J. Thompson was he was about the turn of the century, about 1900. You can see how our atomic theory is really not that old. Okay, about 100 years old. He used a cathode ray tube in order to find electrons inside the atom, and so he found the particle behavior of an electron. And so you can see he had a stream of electrons. This is how we used to do old TVs. We had a positive magnet, a negative magnet, and guess what? He won a Nobel Prize for showing that an electron is a particle, okay, is a particle, and there's these electrons inside of the atom. The funny thing is his son got a Nobel Prize for showing that an electron was not a particle, it was a wave. Okay, there's our duality of nature right there. That's one of my most, that's one of the coolest small facts is J.J. Thompson won a Nobel Prize for showing an electron as a particle. His son, I think it was like 20 years later, got a Nobel Prize for finding that electron is a wave. And so J.J. Thompson found out there were these negatively charged particles, because if it was positive, it would have gone down. If it was neutral, it would have gone straight. It had to be a negatively charged particle. And so he came up with what's called his plum pudding model. But you guys don't know what plum pudding is, because no one has eaten plum pudding for 70 years, or unless you were really constipated. And so I just call it a chocolate chip cookie model. You can see the chocolate chip cookie model. The chocolate chips are the electrons. The cookie part is a positively charged matter, and this was now the atom, the new model of the atom. You can see Dalton's view of the atom. There's disadvantages to this. There's nothing inside of it. They all look the same, right? There are advantages to it. The advantage of J.J. Thompson's model was there's these negatively charged particles called electrons. The disadvantage is, where are these electrons? Are they just out in this place here? Okay. Well, came along Robert Millikan. Robert Millikan used an oil drop experiment, and so what Robert Millikan used an oil drop experiment to calculate the charge of an electron. So he sprayed a bunch of oil drops. These oil drops, gravity pulled it down. He used positive and negative plates in order to suspend an oil drop right here. And he was able to take a look at the electricity that he was using to do the positive and negative plates, and when he did the slope of the line, he always got the same slope. The slope ended up being 1.6 times 10 to the negative 19th coulombs, and so we knew the charge of a single electron. Once we knew the charge of a single electron, we knew the mass of electron, 9.11 times 10 to the negative 31st kilograms. An amazingly not very massive particle at all. Well, came along an English dude named Rutherford. Ernie, he used what's called a gold foil experiment. Okay, and so with the gold foil, what he did was you can get very, very, very thin gold foil, and so you have all these little almost elemental atoms of gold. So gold. It's basically just atoms of gold. Okay, and so if you have all these atoms of gold lined up next to each other, and you have he was able to emit alpha particles. Okay, so positively charged particles. These positively charged particles should have bounced straight back. Okay, should have bounced straight back. If the cookie was all positive, this positive particle of this alpha particle, as it shoots in, should just bam bounce straight back. But in looking at a screen, most of it went straight through, which mean he concluded that the atom was mostly empty space, like some of my students' heads. And so mostly empty space, when I'm talking, of course, not at other times, but most of it went straight through, which meant most of the atom was empty space. But there, every now and then, bing, 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 deflected or reflected this positively charged particle, which meant that there was a positively core center, which they called a nucleus. And so Ernest Rutherford, his experiment, found out that the atom was mostly empty space, and there was this tiny, very massive positive core, central core called a nucleus. Okay, and we're getting closer and closer and closer to our modern model of the atom. And so Ernest Rutherford's, you've seen this before, the electrons are on the outside in this empty space, the positively charged particle right here of the nucleus. The atom is mostly empty space. And so, but we usually think of something very, very massive as something very, very, very big. But guess what? This massive core, which holds almost all of the mass of the atom, this nucleus is really, really, really small. And so you can see how I mean, if you had a grain of sand, the closest electron would probably be on the other side of the county. That's how much empty space is in here. Now, this has a great advantage. Ernest Rutherford's model of the atom, great advantage. You know the nucleus, you know that empty space. These are the two advantages of the Ernest Rutherford model of the atom. The disadvantage is, where do these electrons go? Where do they go? And so along came a guy named Niels Bohr. Okay, he took a look at hydrogen gas, one of the simplest things, and so he heated it up, and he found that there was these things called orbits. We've already studied atomic energy levels, and so he said, you have an electron, you shoot it with light, that electron excites up. When that electron excites down, it gives off energy in the form of light. And so there were quantums of energy. And he called these orbits, not the gum, the orbital energy levels. Okay, and so all he needed to do was he could figure out, since he knew the light, he was able to find out the energy, he was able to find out the energy levels. And so Niels Bohr had a brand new model of the atom. Okay, he used Ernest Rutherford's model of the nucleus, and he found out these energy levels. And so this had another advantage. The problem was when people asked him, well, what do you do with helium? Helium has 2 electrons. Where do you put the second electron? Do you put it on the n equals 1? Do you put it on the n equals 2? Where do you put this second electron? And he couldn't figure it out. So it had a disadvantage of it was limited to hydrogen only. And then in our modern era, which means the 1940s or 1930s, and we started taking a look at even some more concepts of the atom. Now here we have a picture of the United States, and this United States, obviously, how do I know it's the United States? Well, this is a satellite picture from the International Space Station at night of the United States. Now, can you see all the people in the United States? You cannot. But what can you see? You can see probably where the most people live. You can see Atlanta right here. You can see, of course, New York right here. You can see Philadelphia right here. You can see all kinds of different, you can see LA. You can see all the different, where the most people live. Now, my family, my parents live in Philadelphia. So they live right here in Philadelphia. Are my parents in Philadelphia right now? Probably. Probably. It's the coronavirus. They're having to stay in their house. But could they be over here? Yeah, they could. But it's a very low probability, isn't it? Because they live in Philadelphia. Now, do you know exactly where my parents are in Philadelphia? No, you don't. You know with a great probability where they are. Could they be in Ocala, stuck in Ocala with us? Possibly. But a low probability. Could it be in Mexico? Yes, but low probability. And so it's all about probability. And along came a German dude named Werner Heisenberg. And Werner Heisenberg came up with what's called the uncertainty theory. He said it's impossible to know the position and velocity of an electron at a particular instant because of the wave duality of nature. As soon as you take a look at the particle-like behavior of an electron, it behaves like a wave. When you look at the wave-like behavior, it behaves like a particle. And so you cannot know exactly where the position and velocity of an electron is, but you can know the probability. And so it gave us what's called the Electron-Cloud theory. And they said electrons are not in these things called orbits. They're not in these n equals 1, n equals 2 orbits. They're in these things called orbitals, which gives a probability. Which means, as we can see, is the electron right here? Well, there's a high probability because do you see the density of it? Could the electron be out here? It could be. Could it be right here? A little bit greater probability on the outside. So the darker we get, the more probability. In the same way, we can take a look. The electron is probably in this region right here. Okay, could it be out here? Yeah. Could it be in New Jersey? Sure. That's why, Mr. Aiden, I would have failed those elementary school atom projects where you had to build the models of the atom, because I would have just brought in the tiniest particle I could, a piece of a grain of alum, and I would have said, well, this is my nucleus. My electron is there. No, it's no there. No, it's in Atlanta. No, it's in DC. No, it's right next to us. Oh no, the electron's constantly moving. We don't know where the electron is, but we know with a high probability of where it is. And so you can see how our 5 main views of the atom, we have Dalton's view, we have J.J. Thompson's chocolate chip cookie model, Ernest Rutherford's nucleus and empty space, Bohr's energy levels or orbits, and our modern electron-cloud theory of orbitals or atomic theories. And that is the scientific models of the atom.